Greetings and welcome to the United States Transhumanist Party Virtual Enlightenment Salon. My name is Gennady Stoliarov II, and I am the chairman of the U.S. Transhumanist Party. Here we hold conversations with some of the world's leading thinkers in longevity, science, technology, philosophy, and politics. Like the philosophers of the Age of Enlightenment, we aim to connect every field of human endeavor and arrive at new insights to achieve longer lives, greater rationality, and the progress of our civilization. Greetings, ladies and gentlemen, and welcome to our U.S. Transhumanist Party Virtual Enlightenment Salon. Today is Sunday, May 31st, 2026, and the subject of this salon will be of interest to many of our viewers, particularly our longtime viewers. We are going to be discussing cryonics or biostasis, which is a newer term for that field, and recent advances that have occurred within it during the current decade of the 2020s. So joining us today, in addition to myself, is Ramon Garcia, our U.S. Transhumanist Party Director of Visual Art, and our special guest today is Aschwin de Wolf. He is familiar to many of our viewers because we held a highly engaging virtual enlightenment salon with him on December 13th, 2020, when we spoke for 3 hours and 47 minutes on his extensive knowledge of the cryonics field. He provided an overview of various cryopreservation protocols and approaches and considerations for individuals that they should take account of when they're choosing a particular cryopreservation approach. So I caught up with Aschwin at Vitalist Bay in Berkeley, California in mid-May. We were there both on May 17th during the special day that was dedicated to biostasis. And we thought it would be a good idea to follow up on our prior virtual enlightenment salon. And Aschwin is one of the world's leading cryonics researchers and writers. His knowledge of the biostasis field is encyclopedic. And if anyone can tell us what has been happening recently in the field in a comprehensive manner, it is Aschwin. So a bit about him. He is the CEO of Advanced Neural Biosciences, which is his longtime company. You can find it here at advancedneuralbio.com. And he co-authored the first comprehensive human cryopreservation procedures manual. He wrote the first medical biostasis protocol and has edited several books and magazines about human cryopreservation. He is also the president and chief executive officer of Biostasis Technologies, a human cryopreservation research and development organization. You can find that at biostasistechnologies.org. And Biostasis Technologies also has an online newsletter that I would encourage everyone to look at. It is the Biostasis Standard, biostasis.substack.com. And moreover, Aschwin is the owner of another website, biostasis.com. That should be easy to remember. It's Biostasis, the Science of Cryonics, and it hosts a lot of his writings. So please check out these websites. Check out our previous 2020 salon if you have not seen it yet, of course, after you watch this stream. But this salon is a bit of a follow-up on our 2020 conversation. So Aschwin, welcome. And please tell us, in your view, what have been some of the noteworthy developments in cryonics or biostasis since we last had you on the Virtual Enlightenment Salon?
Yes. So I think there are two things you mentioned in your introduction that could be a good vehicle to discuss these things. One thing you mentioned is sort of the more common use or alternative use of the word biostasis. And the reason for that is that there are actually two major ways in inducing metabolic arrest. One is low temperatures, and the other one is chemical fixation. I mean, in the future, there might even be more exotic ways of doing it, like sort of nanotechnology, normothermic biostasis. But sort of right now, these are the two approaches. And I think since the last time I was on this show, the chemopreservation organizations have really stepped up. So now often we sharing sort of the same rooms and sort of talk to each other. So I think, and that might be a really interesting topic of this conversation, sort of how have these two approaches evolved, right? I think maybe the last time I was here, it was more like, well, these people just wrote a bunch of papers and did advocacy, but now they're sort of real organizations who do casework. So that provides, I think, a much more interesting reality check about the merits of both these technologies. So I think that is one thing that happened, and the field has just also really grown. I think. I mean, you always like to say that, like, oh, it's trending, but there are just a lot more entities. If you look at Tomorrow Bio, they are now, I think, the second largest sort of cryonics organizations in the world. And what is it, like five years ago, they were barely existing. We were actually wondering it would ever be possible in Europe to have any kind of credible cryonics organization. Sort of here we are. I think Emil does a really good job of putting them on the map, and they're available in the United States as well. So I think the field in general has grown, and the ways in which we induce metabolic arrest, there are different approaches now, and some people favor one and some people favor the other, and not necessarily always very informed, I might say. So that's sort of a good sort of topic sort of to bounce around. And I think the other thing I want to mention is that it has become more common to see cryonics or cryonics adjacent papers showing up in more sort of respectable journals, whether it's review papers or new work. The Society for Cryobiology, I think, is sort of becoming a little bit more comfortable with sort of the more serious sort of researchers in our community. So yeah, these are some of the more interesting trends at the moment, I would say.
Yes, thank you for that overview. And it's interesting you mentioned the growth of the field, both in terms of a new large biostasis organization, Tomorrow Bio, taking hold in Europe and then scaling up its operations internationally, as well as the mainstream discipline of cryobiology becoming more receptive to cryonics. I know, for instance, Greg Fay, who is also one of our previous guests, when he originally appeared on our salon in 2020, he wanted to be very careful to only talk about the science of cryobiology. He didn't want to talk about cryonics at all, even though he's very much involved in cryonics related research, because he was afraid of the reactions from his colleagues. But since that time, he became the president of the American Society of Cryobiology, and it seemed that he was more willing to openly discuss cryonics. It seemed that the taboo on that within the cryobiology field was no longer nearly as strong. So I'm curious as to why you think that happened. Why in this decade, it seems, at least in terms of mainstream respectability or being recognized as a serious scientific pursuit, cryonics or biostasis really gained ground. And of course, we mentioned the term biostasis as perhaps trying to set up that framework for greater mainstream scientific acceptance. Do you think that has contributed to a great extent, or has it been more of kind of a follow-on action from greater acceptance that came previously?
Yeah, that's a really good question. And one thing I want to mention sort of in this context, I think we tend to think of this relationship with mainstream cryobiology as like, it was really bad and sort of now it's getting better. But actually in the really early days, there was a lot of interest actually from mainstream cryobiologists sort of for this as well. But I think when they found that there actually was not a whole lot of funding forthcoming, that is, I think, where sort of a lot of the more hostility sort of took ground. And maybe some of the ways those people talked to each other in the 80s, even from our side, was maybe not the best sort of we could have done. But I would say it's not, I wouldn't say it's back to sort of how it was, but relationships have been better. It was really, I think, in the 80s and 90s where it was like really, if you forgive me the phrase, like really cold, and cool. I think I think there are a number of reasons sort of why it's changing. I think at some point, you talked about this sort of, this sort of double life of some of the people sort of in cryobiology. And at some point, people just will figure out like, wow, these people who originated sort of in cryonics, they've contributed a lot actually to mainstream cryobiology. That is, I think, one of the talking points that is very important for us to emphasize, to say like, look, even if you don't agree sort of with sort of the ultimate objectives of cryonics or biostasis, what we're doing can help with mainstream organ preservation. It can help with brain banking, sort of, and so forth. And if you really make a compelling case for that, I'm like, yeah. I think another thing I'm seeing is that instead of just sort of, dismissing it, it's more like, okay, show me the evidence. And that is a reasonable request, right? So I think that's sort of also happening as well. And I mean, the third thing is, and that is, I think, particularly interesting sort of for your audience, right? People are getting more and more comfortable with technological developments that we sort of would rule out sort of in the 50s and 60s. Like, for example, the use of AI to reconstruct a normal brain from a damaged brain. I mean, we know that these technologies are in the pipeline already in silico. We probably can do a lot of that front. And so people are starting sort of putting these sort of pieces together. So I think all these things sort of matter. But I think it's also a personal thing, like who exactly is running the Society for Cryobiology and who are the cryonicists, right? They're dealing with. And, if these are good people and have a cooperative spirits, it's, it's better. I think the internet has also sort of changed a lot. I think it used to be the case, well, if that journal doesn't accept your publication, it's over. And now it's like, well, I just take it somewhere else, or maybe I just put it online for some alternative kind of peer review, or blockchain based publications or stuff like that. So the way we publish things is also changing.
Yes, indeed. And to your point, the diversity of sources that people can access has increased to an immense extent. And there are also more venues for longevists more generally, but cryonics advocates or biostasis advocates as well, to explain their ideas, to present them. There are now multiple conferences every year, and Vitalist Bay that we attended was among them. The use of artificial intelligence, including in biostasis, is proliferating. So in November of 2024, we held a virtual Enlightenment Salon with Alex Crouch, a gentleman who founded the Revival Research Group, and he puts out publications regularly, essentially using AI to help project what revival from biostasis would look like in the future. So we had a fascinating conversation with him on that. Now, organ preservation is one subject I wanted to delve into further, and I think this is a great opportunity because you're correct. Even for people who don't accept the premise of, say, whole body human cryopreservation, they could be brought to see the merit of advancing the research because there's a shortage of donor organs. And even without, say, 3D printing genetically identical organs to the recipient, if there is a given donor organ, but it's 2,000 miles away and it's necessary to ship it to the patient in good condition, being able to preserve it with really high fidelity could save a lot of lives. And to that point, Greg Fahey demonstrated several years ago that it was possible to vitrify a rabbit kidney and then transplant it back into the rabbit, and the rabbit was alive 2 years later, last I heard, and functioning the way a rabbit should. So perhaps that has contributed to the prospects of greater viability of donated organs more generally. But what are your thoughts on that, and how the biostasis research field can help with this very pressing problem that exists right now, and perhaps also thereby gain even more mainstream acceptance?
Yes. Yeah, absolutely. And I think it is already the case, right? And that is sort of, to me, the article that has never been written yet, but should. It's like, if you really look carefully, sort of who are the people behind these advances in complex mammalian organ preservation or perfecting brain preservation, even if it's for pharmaceutical studies, you will end up in sort of our community, right? So even without the whole sort of cryonics angles, I think it's undeniably the case that a lot of the concept we take for granted sort of in cryobiology, like modern vitrification technologies, the way we think about cryoprotectant toxicity, perfusion technologies, a lot of that goes back sort of to this community, right? And you see that sort of a lot in modern technologies that if you really start going back, you see it with the extropians as well, right? Sort of with AI or cryptocurrency, that there was this sort of group that were really on the fringe, it looked like, but now sort of these things are becoming more mainstream and starting to trend, and hopefully, yeah, that is contagious, and now more people at universities feel like, okay, organ preservation is actually within reach, or at least it's not something that we completely need to give up on. I think there was a while where it was maybe only Greg and a few other people who were pursuing that, and that has changed. And to sort of circle back to what we're saying about like the Society from Cryobiology, if you go to like an event like the Vitalist Bay, you hear some presentations that is like state-of-the-art cryobiology, right? So it's no longer the case sort of that these groups completely control the message, right? So we're contributing. But of course, it does remain a formidable challenge, right? So right now, Brian Woke at the Vitalist Base showed a really interesting slide where he said, like, right now, we can reversibly vitrify sort of an organ like about sort of 1 centimeter. So there are scaling issues. It's still not ready sort of for prime time sort of in humans. And hopefully technologies like AI or more groups and specialists working on that can push this lab work a lot more sort of into the the clinical realm. Yes.
Yes. So speaking of these scaling issues and these obstacles, this leads into an area of curiosity that I have, and I will try to ask about this in regard to every subset of cryopreservation technologies that we will discuss today, and that is, what kinds of advances could be seen as major incremental progress? One of the points you made at Vitalist Bay is that it's not really reasonable for the public to say, well, I'll believe in the viability of cryonics when a small mammal has been brought back from biostasis, because that's actually almost as complex as bringing back a human. And if we are able to bring back a small mammal, we would be quite close to bringing back a human already. But we don't want the public to only be on board when we're 90% or 95% to the goal. We want the public to be on board when we're 25% of the way to the goal and people can see some tangible achievements. So in the area of organ cryopreservation, for instance, I would envision if we start seeing a lot of cryopreserved organs making it to patients, a lot of successful transplants that enable these patients to live much longer and healthier lives, that could be one of those earlier milestones. But you mentioned Brian Woke's comments about the scaling issues. So, what kinds of approaches along the way do you think would need to arise in order to resolve those scaling issues? And approximately how long do you think it would take, given enough dedication and investment, to actually start seeing this scenario that I described occurring routinely?
Yeah, I think that the scaling issue is really interesting, because in one way, one could argue that the small scale does not matter much, in the sense like, well, if you cannot reversibly cryopreserve, the lungs, the heart, all the organs sort of that matter, uh, then it's not gonna. I mean, it's just as hard sort of with a small animal, because things like cryoprotectant toxicity, they don't care sort of whether you're talking about sort of a big organism, big organs, or smaller organism. It's sort of the same mechanisms, but there are some reasons why sort of the scaling is harder, and I can think of a practical one and sort of a technical one. The practical one is simply it entails sort of large animal work, and that is increasingly sort of not common sort of in academia to do. Let's say cryopreserving organs of pigs or dogs or whatever. So it's just not there. Not many sort of labs that do that, right? So that sort of holds back the progress. And on a technical, the one thing where the scaling thing does matter is, of course, in warming, right? Because if you have something teeny tiny and you can just warm it up sort of by passively sort of warming it up, that would be way too slow for a large organ. So that's why people exploring different warming technologies. I mean, the most basic one is, of course, a very simple convective sort of surface warming, but that has limitations, because by the time sort of the core of an organ is at the right temperature, the outer parts of the organ have already been exposed to very warm temperatures, and you get all the cryotoxicity that comes from that sort of downstream. So people have been looking into like nano warming, right, where you just perfuse these sort of particles inside an organ, or perhaps even the whole body, and then you can sort of uniformly sort of warm that up. And there's sort of there are pros and cons about that. And then there's dielectric warming. That's actually Brian Woke sort of the technique that they're using mostly at 21st century medicine. So warming is going to be very important to be able to scale from very small organs to large organs, because, as I said, you cannot have a situation where the core of an organ is still really cold and the exterior is really warm, and then you get your ischemia, and then you get your cryoprotectant toxicity. So that is going to be sort of a major challenge. One thing I want to mention is, and I think that's sort of really important, right? So the role of this kind of research for the credibility of cryonics. I think for cryonics, or sort of any kind of biostasis, it's usually sufficient to just show like, oh, viability is reasonably well maintained, or here's good ultrastructure, and then sort of future technologies might be able to infer sort of the original state or viability from that. And I think that is one of the biggest sources of confusion, I think, about the relationship between mainstream cryobiology and cryonics. It sometimes is assumed, unless you have reversible true suspended animation, cryonics not sort of credible. But of course, if we would have that, that would almost sort of render cryonics sort of irrelevant, right? So cryonics always has that element of uncertainty, where we say like, okay, we can do a reasonably good job in preserving structure and maybe some degree of viability, but we are expecting some reasonable progress in science that can advance up to the point when these patients can be revived. And the beauty about either low temperatures or like really good chemical fixation is you produce complete metabolic arrest, right? So it would be hard to imagine that technology comes to a complete halt, right? So most of the issues resolve more around like, okay, is this socially sustainable? Like, is it possible for people to be in storage for such a long time? And of course, what that time is, that is very sort of subjective. In fact, I think you asked me about that. What is sort of the trajectory sort of organ preservation? And yeah, I find it hard to say. If we would just extrapolate cryobiology of the last 40 years, I would say very long, right? Because it has taken a very long time to even get to reversible cryopreservation of, say, a kidney. And there are organs are actually quite a bit harder, like the lungs or the heart. On the other hand, more people are working now in this field, and there's a lot more funding flowing into this field. And then we have AI, right? So far, I'm not aware yet of that sort of transforming the field in really impactful ways, but it's hard to imagine how it could not. And I think one area where I think it could be really useful is in the discovery of new cryoprotectants. I think the major roadblock for reversible organ cryopreservation or even human suspended animation is that these cryoprotectants do a really good job of inhibiting ice formation, but it comes at a price. They have some sort of degree of toxicity, and exactly the mechanism is kind of a pretty complex field. But you can only expose organs for a certain amount of time to these cryoprotectants, and you have to do that at sort of low temperatures. That really restricts our flexibility with these kind of solutions. We cannot just keep perfusing for a very long time until all the parts are equally well perfused. So we're really running against sort of time and temperatures. But one thing I find interesting about the field of cryoprotectants and cryoprotectant discovery, it has always been a little bit like, okay, these molecules have favorable structures, and let's just try them, just a lot trial and error. Using AI to maybe reverse engineer from what would be favorable properties to a cryoprotectant to new kinds of structures, molecules that can be synthesized, that should have promise. I'm not aware yet of that sort of producing breakthroughs right now, but I mean, how long are we with this, applying AI to this? The really, really strong AI is pretty young in that regard. And there was actually an interesting presentation about it at the Vitrification Bay as well, when someone said, well, biology, that is the real sort of test case for AI, because these are really tough problems, right? Sort of, we all know these enormous diagrams of human metabolism. Is like, oh, try to figure this out. But yeah, I can't see. It's hard to not imagine a scenario where I would be a lot more useful in the discovery, identification, and maybe even helping into synthesis of new cryoprotectants. And if we could find, and that's sort of the holy grail of cryobiology, a cryoprotectant that is non-toxic regardless of exposure time and temperature, then all bets are off, really.
Yes, many fascinating remarks there, and many tie-ins to what we heard at Vitalist Bay as well on the subject of AI. We did hear a presentation by Dr. Dario Unutmaz, who is one of the foremost advocates of using AI in medical research, and he actually presented slides that were AI generated, but he was discussing various applications and how they have risen just in the past few years. But to your point, generative AI is quite a young technology, and we are all still learning how to use it, from just asking simple one-time queries to perhaps generating material ourselves to AI agents, which people are increasingly putting to use, that can be essentially sent off to do various tasks and perform
Mhm.
research and analysis over a range of documents or applications. And I think in terms of how those agents could be harnessed, of course, hopefully prudently in ways that minimize any unintended consequences like them deleting all of one's files, there could be a lot of potential there. Again, once people learn what works, what doesn't work, what some of the limitations are, like with early generative AI, hallucinations were a huge limitation. And
Mhm.
that underscored the importance of the human in the loop, of understanding what the AIs can do well and where the AIs are still limited. And before we go into the specific technological considerations you mentioned, I'm curious as to what your observations have been in terms of where AI has been a valuable contributor to the biostasis field versus where it's perhaps premature to apply it, or where people have made mistakes with it. Like in the legal field, it's well known people have
Mhm.
submitted legal briefs with hallucinated cases that didn't exist. Hopefully,
Yeah,
nothing
yeah.
like this happened in the biostasis field. But I'd be curious as to the general thoughts you have on both the good use cases and the limitations.
Yeah, actually, I was just thinking about it sort of when you were talking about this, and um, one area where AI is really really helpful, and that's maybe often when people think about AI, they often think about right problem solving or like coming up with, well, as we discussed, like new molecules. But where AI is particularly useful, undeniably so, is like really speeding up the efficiency in the lab, right? So let's say you want to compare 8 different molecules, and then you can just feed it, and it can just say, okay, be careful with your pH in this one, use a buffer in that one. I mean, of course, we're smart enough to research it ourselves, but that takes a while, right? So just very practical questions, sort of how to model something. I found it sort of pretty reliable. Yeah, as you said, when it comes to like what I would call creative science, like really saying things that like, oh, I've never thought of that. Yeah, I have not seen that yet so far. In fact, when I sometimes try to ask a sort of quasi-creative question, sometimes I can just see that it's drawing upon sort of my own writings or manual and sort of answering me, and that is sort of, partly sort of somewhat flattering, but it's like, yeah, okay, I sort of, you're telling me about something I've written myself. uh, so when it comes to, yeah, to creativity, not yet, but I think it will, I think it will get there sort of, but in terms of just practical problem solving, bringing information together, if someone wrote a long PhD thesis about a topic you're really interested in, but they're like, I want to see the take home points here because I want to use that in my own lab. I mean, you can have that in a couple of minutes, right? And that has been sort of very beneficial. But yes, and sometimes, of course, we know this, you have to fact check some of that stuff, right? Sometimes it can say really, really sort of wonky things, right? But yeah, but yeah, true creativity, and I think that is an aspect that is sometimes sort of ignored, sort of in when people talk about science, right? There's like, on the one hand, there are artists, and on the other, that's scientists who just observe. But coming up with theories that sort of link a lot of sort of random phenomena is itself often a creative act, right? So that is, I think, where AI still is, I think, sort of lagging in coming up with sort of really, I mean, I've done, my fair share of queries, and you never see like, you know what? Why don't you try this? And this might be a very interesting way to do that, and something really novel. I have not seen that really so much in my field yet. I mean, it might be other people have seen it in their own fields, but that stuff I have not seen yet. It is more like, if you feed it something, it can process it sort of really well and summarize things and take a lot of boring work out of your hands. But I think the really true creativity that is required to maybe solve some of these problems, sort of really novel theories about how things work, yes, that still has to come, if it will. But yeah.
Yes, and those observations definitely resonate with what I have seen in terms of at least the current large language models, the current generative AI systems. They're excellent at synthesizing or integrating content, particularly if you give them reference materials. For instance, Google's Notebook LM is very good at that. Instead of just putting things together from the open internet, if you give it an area of content to focus on, if you give it particular readings, particular videos, even many of them, it can provide some very coherent narratives and analysis of this. But to your point, the AIs draw on source material, and that source material was created by humans and put onto the internet by humans. And sometimes if you are an advanced subject matter expert in your field, as you are in the biostasis field, then the AIs aren't going to tell you anything you don't already know. They might save you 2 hours of work in terms of synthesizing ideas that you already know, but you have to take an idea from this paper that you know about, take an idea from this other paper that you know about, in order to just write about the current state of the field. And the AI can do that for you, leaving you more time for your truly original insights. And I've been telling people this for years. AI is not going to replace in-depth human subject matter expertise. It's only going to make that expertise more important, precisely because a true expert can see when the AI output has some issues with it that may be too subtle for a layperson to detect. So I think your work in particular is going to be crucial to the advancement of the biostasis field. So one aspect that you already mentioned that I would like to delve into greater depth on would be the cryoprotectants, both the cryoprotectants that are currently in use today and their respective levels of both efficacy and toxicity, as well as any either recent advances that you've observed or prospects for the not too distant future for there to be a better cryoprotectant. By better, I mean either one that is less toxic or one that achieves just a really high quality of cryopreservation with the same level of toxicity as currently, at least not any worse than currently.
Yeah, absolutely. That is actually a field where you don't hear a lot of new stuff. And what I mean by new stuff is like a cryoprotectant, let's say, that you've never heard before, right? So like in the 60s, there were review articles of like, okay, what are sort of all the different cryoprotectants and their properties? If you look at let's say the vitrification agents that are used in biostasis today, usually it's just a combination of these cryoprotectants. Of course, there's been a lot of research in sort of how to combine them and how much to use of what. I mean, sort of the era of using one cryoprotectant is kind of sort of over, especially because of a phenomenon that Greg Fay identified in his work, and that's called cryoprotectant toxicity neutralization. So if you combine two cryoprotectants together, they can have lower toxicity than the same concentration of these cryoprotectants alone. And various sort of mechanisms have been sort of proposed for that. So that's sort of really interesting. But a lot of the cryoprotectants we use today, there are no like, oh, what? I've never heard of that molecule, right? I mean, there is some interesting stuff going on with people sort of modifying or straight up using molecules that are used in, let's say, hibernating animals, or the Canadian wood frog can go sort of to sub-zero temperatures. I personally think often these molecules are too big to use them as a mono agent, and they're often extracellular, right? So it's not like it's not like something you can just run with and do away with all the sort of old DMSO and glycerol and all the older cryoprotectants we have. But there might be a place for it. But I mean, we're going to see that hopefully soon. I've heard sort of people working on true neo cryoprotectants, and either maybe somewhere discovered by serendipity, like, oh wow, this actually works better than we thought, or they reverse engineered from like, okay, these are the ideal properties that a cryoprotectant need to have, like no or low toxicity, low viscosity, not too toxic to deal with, to handle, and then sort of see what that yields, and whether discovery through AI can play a role in that. That is, I think, yeah, we're going to see, I think, not too long, because now there's a lot of hype, right, about sort of especially in pharmaceutical industry, you see that, and whether that sort of hype will translate to cryobiology as well. But yeah, we made a lot of progress, but I will say a lot of it is by combining the molecules that we already know. Some industries, they're always pumping out and synthesizing new molecules. Of course, the pharmaceutical industry, in which they have like sometimes like tens of billions sort of to look into that. I mean, of course, we don't have these kind of resources, right? So that's why we're sort of always tinkering with sort of existing molecules. But there are also fields that are much worse in that regard. If you look at morticians in the funeral industry, that have basically been using sort of the same molecules sort of forever. There is not a very active research field in formulating, let's say, new ways sort of to embalm people. Like, okay, there's a little bit more emphasis on green embalming and so forth, but that's not where the hot chemists will find sort of employment. But hopefully, with the greater recognition of our field and sort of the limited breakthroughs we have, there will be a lot more, let's say, chemists, computational people, and coming to this field, and let's say, okay, what exactly is cryoprotectant toxicity, right? Because cryoprotectant toxicity is a little bit like aging, right? If you put 3 aging researchers in a room and you ask them what aging is, then you get 3 different answers, and they're like, okay, that doesn't sound promising for the field if you already disagree on the definition of field. I think we're a little better in that sense in cryobiology. Most people do agree sort of what works, what the problems are. Cryobiology, cryoprotectant toxicity is still not sort of completely understood, but especially the lab of Greg Fay and Brian Woke, 21st Century Medicine, I think made some really interesting discoveries that indicate what some of the mechanisms are. One big one is, to get a little bit more technical, is what they named the perturbation of hydration shells of proteins. Like water, of course, is bad, right, if you want to go to very low temperatures, but proteins have a hydration shell that keeps them stable, right? And if you have a very strong cryoprotectant, it can disturb that layer of proteins, and that's not good. So actually, they came up with a metric called QV that allows people to predict the general toxicity of a cryoprotectant solution. Now, feeding that stuff maybe into sort of AI and allowing them to do these calculations with a whole bunch of molecules, yes, I mean, that there might be some interesting research over there. But I think the real paradigm change would come when people say, like, okay, now you're mixing, we're going from mixing these molecules that we already know in different ways to like, oh, I've never heard of this. I've never heard of this approach, right? And then suddenly you have a paradigm change. That happened maybe a little bit of warming. That's not really sort of my wheelhouse, but like sort of with the nano warming, that was sort of really interesting that this group was able to sort of recover a rat kidney, and they used nano warming instead of the technology that 21st century medicine is using. So that sort of kind of paradigm sort of shift sometimes can be very powerful. But I think we're just at the beginning of that right now. I work in the field. I don't see people dabbling with all these sort of new exotic sort of molecules, but it must happen, I think. Yeah.
Yes, and it's interesting, the nano warming breakthrough that you mentioned seems to have occurred in 2023. The title of the paper that I'm seeing is Vitrification and Nano Warming Enable Long-Term Organ Cryopreservation and Life-Sustaining Kidney Transplantation in a Rat Model. So I will post this title here. And it's interesting. This was published in Nature Communications. Quite a few researchers involved in this. The lead researcher is Zhonggu Han, Han. So a worthwhile paper to explore. I will put up the link to it. How would you say this was received in the biostasis community when this research came out? And could you perhaps compare and contrast nano warming with prevailing approaches to warming that have been used up to this time? You mentioned the dielectric warming. Has that been the predominant approach, or have there been other approaches as well that have previously been posited as the likely ones?
Yes, absolutely. I think that paper stood out, I think, for a number of reasons. I think up until that point, it was basically just like 21st century medicine was doing, mammalian organ cryopreservation. And if you wanted to know if that was successful and where we were, that you had to go there, and then they gave you an answer. And then we will just, hope that they make sort of more progress. And of course, they I think are still sort of the leading lab in the world for sure. But it was very interesting to see a paper coming from a very sort of different sort of academic institution. And then another thing was interesting is they use a different animal model, right? So they do the rabbit in 21st century medicine, and they did the rat, and they were able to, repeatedly vitrify an organ. And then they used a different warming technology, right? The nano warming. Now, to your question about sort of what is sort of the prevailing and sort of the mainstream approach or before that, well, the short answer is actually that there are not many labs or academic institutions that do sort of large organ or mammalian organ preservation. So there was never a whole lot. But aside from doing something very crude like just doing normal convective sort of surface cooling, dielectric sort of microwave rewarming, where you just use like high frequency electromagnetic waves. That is sort of the technology that 21st century medicine sort of is using. And there are pros and cons of both approaches. Like what I often hear about nano warming, it's like, well, the cool thing is these nanoparticles, of course, go throughout the whole organ or even sort of the whole body. But if that would not happen, you can have cold spots, or let's say these nanoparticles are very concentrated in an area, you get sort of too much warming, right? So it's like it has the appeal of universal warming without having to worry about, the exterior warms a lot faster than the interior. So that's good about it. But a lot of it really depends on your perfusion technology. If an organ, let's say, is slightly ischemic, these nanoparticles may not be delivered in all the spots that you want, and then sort of you have a problem. There might also be problems sort of with washout. Can you like completely sort of wash them out, and sort of long-term biocompatibility and stuff like that. And and dielectric cooling, as I said, again, this is sort of not really my wheelhouse and what we really do sort of in our lab. I can talk about that sort of a little bit more, but also has that advantage, if not that it's not sort of dependent on exposing an organ, the exterior, to warmth. Is also technology that at least aims to do sort of uniform cooling, but it's technically pretty complex. So there's my understanding. I recently actually was blessed to do a visit to 21st century medicine, and Brian was so grateful to explain a lot about it, and was like, there's sort of a lot going on there. But in the end, there needs to be a very good solution to this problem, right? Because without fast, um, well, I mean, if you would have cryoprotectants that have no toxicity at all, then you can make them also very, very concentrated, and you should not be as concerned anymore about very fast cooling and warming rates, right? Because the reason why you want to cool so fast, the reason why you want to warm so fast is because you want to outrun the tendency to vitrify, to form ice. And if you're too slow, you get ice formation, or during the warming phase, you get devitrification. But if you would have a cryoprotectant, there's actually a name for it. It's called an equilibrium cryoprotectant, that no matter how slow you cool or warm, it can simply not form ice. That would be ideal. But these cryoprotectants right now would be sort of way too toxic. So in the end, it is a cryoprotectant toxicity problem. If we crack that, then we can be a lot more relaxed on sort of all these other things like viscosity, or having sort of the ideal cooling and warming rates and technologies. I mean, we still need to do it, but these requirements are relaxed. So cryoprotectant toxicity remains sort of I think, the number one problem in the field.
Yes, thank you for those insights. One of our viewers, More Life Please, John H., notes, well, microwaves cook things from the inside out. I think this is in regard to the risk of, say, uneven rewarming of cryopreserved tissues, or later on cryopreserved patients. I wonder if you think there could be multiple approaches to rewarming deployed simultaneously. Like if one approach is better at rewarming one part or one system of the patient, and another approach is better at rewarming another, if you could somehow equalize their rates with two or more approaches, so that the end result is that the organ or the body is rewarmed evenly.
Absolutely. And actually, one thing I think I want to mention, because I think that's very important, because it comes up a lot. I think when we're no longer thinking about mainstream organ cryopreservation, but we're talking about sort of cryonics, this issue is not as much of a concern, because sometimes people think like, oh, so that you have this cryopreserved patient, you have a plan for revival, and then you have to warm them up, and that is an enormous challenge. And then while they warm up, there will this additional ischemia, things that were barely vitrified will devitrify, and you get ice formation after all. It becomes a total mess. So we need to master these warming technologies. But one thing that I think is pretty universally recognized in the field of biostasis is that any attempts for revival of patients, a lot of that initial work will be done at cryogenic temperatures, right? I was sort of honored to be able to have Robert Freitas produce this enormous tome, Cryostasis Revival, right? And if you really read that book carefully, a lot of the repair and stabilization happens at cryogenic temperatures. And actually, in some ways, these temperatures favor the operation sort of these kind of machines. So the technologies, maybe nano warming, I don't know, but the technologies that we're talking about now for mainstream cryobiology, I think are not really a good framework for what we can expect, how it will go with the rewarming and repair of cryonics patient, right? So again, really want to refer you to Robert Freitas' excellent cryostasis revival book, because it goes into great detail about how that would go. So you basically would start with doing some very advanced scans at cryogenic temperatures, and sort of how detailed these scans will be, I think, depends on almost philosophical position on this, like, how fine-grained is identity encoded, right? But let's say the most grandiose scenario would be almost an atomic level sort of scan. And then in silico, sort of a comparison will be made between healthy structure and sort of the damaged structure. And then probably some agents will be introduced in the patient at very low temperatures that are still metabolic inhibitors, so that when there is rewarming, gradually more repairs can be done, but you don't get sort of this runaway ice formation problem that you could have in mainstream sort of organ preservation, right? So the sort of the technologies that will be utilized for rewarming and repair, I think that is a very difficult, very different approach than mainstream warming of organs. And I think that's very important to recognize, right? Because sometimes people work in cryobiology and like, oh, I cannot even properly warm up something, the size of this, and how can you even think you can do it with a whole human being? But it's like but that's not what we're saying, right? It's not like, no, these technologies, we have a good idea how they will look like conceptually, right? But those have to be in place for meaningful rewarming and repair of cryonics patients. So it's not, and that's also the reason, like my own lab focus a lot more on sort of optimizing preservation quality for that reason, and sort of advising existing cryonics organizations sort of how to optimize and retool their approaches, because that's where the biggest gains are right now. Of course, I'm not saying like, oh, let the future sort of deal with sort of rewarming and repairs. No, that is a very important topic. But at this point, sort of on this side of the fence, we were really focusing on optimization of preserving the ultrastructure and viability as well as we can. And actually, that might be an interesting topic sort of to talk about, is like how we have progressed in terms of preservation quality, and how other fields like chemical preservation sort of approach this problem.
Yes, I think it would be intriguing to venture into preservation quality quite soon. I did want to point out the link to the book by Robert Freitas. The book is called Cryostasis Revival, The Recovery of Cryonics Patients Through Nanomedicine. It was published in 2022, and it's interesting, when we had you as a guest in December 2020, you kind of hinted that this would be forthcoming. It wasn't available yet, but it is a major work in the field and a major development since we last had you on the salon. Now, before we venture into preservation quality, we do have a question from Art Ramon on what we discussed. He's wondering about ultrasonic warming and 3D temperature sensing of the organ. Are you aware of any studies looking into those approaches?
Yeah, again, so this is sort of not sort of really my wheelhouse, the rewarming side of things. I'm sort of aware of it, sort of, the sort of the high intensity, so the ultra sound. I think he himself, the person asked the question, works with some, warming technologies. So he probably knows more about it than I do. Yeah, so I'm aware of that approach being tried, but I cannot say I'm particularly knowledgeable about sort of that specific subfield.
Yes, and we have another
Mhm.
viewer, Taylor Mara, who writes, great discussion, and I can recommend the Cryostasis Revival book. And her question was, what do you think about the potential of Dr. Risco's ultrasound HISU rewarming approach? So along the same lines as Art Ramon's question, this seems to be another promising approach in the field. So great. We are having some good viewer engagement today, and I think this is a good bridge into your research, Aschwin, into preservation quality, how it can be assessed, how it has improved, and the different approaches that are available.
Yeah, I think one lens that is really important to look at these different technologies is how do they work in the real world, right? So how do they sort of clinically work? And when I started my lab in 2008, I had to ask myself a question like, well, with these amazing scientists like sort of Greg Fay and Brian Woke, doing all this sort of fundamental work in, perfecting organ cryopreservation, sort of what sort of role can my lab play? And one thing I sort of quite easily figured out is that there was not a lot of work going on and research into what are actually the effects on cryopreservation when you assume and try to model real world conditions, right? So a patient can be down for like half an hour or an hour, and we call that ischemia, so the lack of blood flow, the lack of oxygen to the brain. If you then introduce a cryoprotectant, what are the effects of that? And that have been sort of pretty revealing. There has been a lot of research in stroke and the field of like cardiac arrest. It's like sort of what are the effects of depriving the brain of oxygenated blood. And one of the things they found is if you do that for a considerable time, a lot of these vessels collapse, cells become very edematous, start swelling, and you can simply no longer perfuse that brain. Let's talk about the brain for now. You can no longer just perfuse that brain and hit all the spots in the brain that you normally can. And that's interesting because actually the brain, because sometimes you feel, oh, the brain must be so hard compared to other organs, but because the brain has such a high metabolic demand, it's actually really well vascularized. Nonetheless, when you have significant downtime, then you can no longer perfuse all these sort of capillaries and micro vessels well. So your perfusion sort of comes in and sort of goes out, but it doesn't go anywhere. And there's a very easy way to research that in the lab. You can induce a certain amount of ischemia, and that can be cold or warm. And like warm, we often call normothermic ischemia. You keep sort of an experimental animal at sort of normal body temperature, and then later you introduce a cryoprotectant. And what you see is the longer the period of ischemia, the more of these areas of perfusion impairment you have. So you could take that brain and then cool it to cryogenic temperatures, and then then you will find that a lot of these areas are frozen regardless of perfusing a vitrification agent. And that is very sort of important to recognize, right? Because sometimes what you see in our field is like people have various approaches in inducing metabolic arrest, right? So there is sort of the traditional cryo sort of people, and then on the other hand, there are the chemical fixation people. But one of the most crucial questions to ask both, it's like, okay, if you have a more realistic real world clinical case, what kind of results do these different technologies yield? And one thing you'll see, and I talked about it in another podcast, sort of, I think a year ago when I was with Andy McKenzie, and sort of I was the pro cryo guy and he was chemical fixation, although I actually am pretty accepting of both approaches. But sort of one thing we really converged on, it's like, yeah, the brain doesn't really care if you're going to perfuse something with a cryoprotectant agent or with a chemical fixative. If there's a long amount of ischemia, then you cannot get that to go anywhere. Now, there's one advantage of cryo in that sense, like even if you get that ice formation, if you cool to cryogenic temperatures, you still induce metabolic arrest, right? It's still like, okay, there's damage, but there is true metabolic arrest, so you have a lot of time. With chemical fixation, that becomes more complicated depending on your storage temperature, right? I mean, there is quite a bit of unresolved debate in the community is if you do fixation right, if you do it really right, could you store at room temperature? Could you store in a fridge? If not, what should the temperature be? But one thing I think that's not controversial in the field, sort of in both camps, so to say, is if you would have a long delay in before you start your procedure, you cannot universally introduce that chemical fixative. So if you would then store at a relatively high temperature, whether it's room temperature or even in a fridge, over time, these areas will just continue to disintegrate, right? So if you actually look at the field, and this is, I think, a really interesting talking point, the field of chemopreservation, there are now two companies, and they take, in my opinion, a very different approach to this. So there is Sparks brain preservation. And a lot of their cases are non-ideal cases. And what they do is they actually take the brain out of the skull and then immerse it in a fixative, right? And if you do that for a long enough time, then the whole brain will be fixed. But that takes a considerable time, and we actually don't know exactly. You would think, well, we just know how long that takes, but measuring that is actually non-trivial. But during that time that you immerse that brain, of course, there is especially ischemia, called ischemia, in sort of the core of the brain. So it's one thing to say, oh, we have these great sort of electron micrographs of chemically fixed brains. Why would anyone choose any other technology? But when you try to do it sort of in the real world, yeah, there are complications. Now there is Nectome, also in Oregon, in Pacific Northwest. It's actually pretty interesting that three major biostasis initiatives, Sparks, my own lab, and Nectome, were all in the same 100-kilometer sort of radius, sort of in the United States. That has been a very interesting development, but that is an aside. Their approach is basically, well, we only do chemical preservation under very controlled circumstances. So what they mean by that usually is a right to die case, which of course is legal in Oregon and Washington, in which you can start your procedure right away. So they hope to produce sort of the same results or very similar to what you sort of can do in the lab, right? So this is, I think, one of the most important considerations when you compare technologies. It's like, okay, under which conditions do they occur? And if they are somewhat different from your typical lab situation, and usually they are, people, die out of hospital, camping trips, or alone in their home. How are you going to apply these technologies? And that is, I think, a very evolving part right now in the field. There's a lot of sort of crosstalk between sort of the traditional cryo people and the chemical fixation people. It's like, okay, how do we deal with these sort of suboptimal cases? And that's not completely clear. For example, one research project that my company is sort of involved in is to really compare this sort of immersion fixation, where you just put the whole brain in a fixative, comparing against a straight up sort of straight freeze. Now, straight freeze is like the last thing you want to do from a cryobiology perspective, right? But on the other hand, if you immerse a whole brain in fixative, I mean, that diffusion, takes days, weeks, and some people even say months to get to the core of the brain. Does it look worse at an ultra-structural level than even if you would do a straight freeze? So these are some of the really practical questions that sort of the larger field is dealing with right now. And I think it also has sort of brought the field sort of together. I mean, you may still recall from maybe 10 years ago, or sort of with sort of the first studies in aldite stabilized cryoprotection. It's like, oh, why would you even still deal with sort of classic cryo, right? But I think increasingly, as these technologies are being implemented, we have a lot to talk to each other, because you're dealing with the same problems. As I said, the brain doesn't care, whether it's going to be perfused with cryoprotectant and a fixative. It's very ischemic. You have sort of the same kind of effects in the brain. And we do have a lot of experience in the traditional cryo field in thinking about sort of what are the best sort of approaches given a certain clinical condition, given a certain downtime. Yeah.
Yes, and I recall discussions of this during the panel at Vitalist Bay, where you participated and others representing the chemical fixation field, like I think it was Boris Robel of Nectome, and then Mr. Sparks also participated in that one. And there was a discussion about this 12-minute or 12 to 18-minute time window that Nectome believed that it needed to have essentially after the patient's death in order to successfully achieve perfusion using its own techniques. But it was mentioned that this was really not an outcome of just the natural decay of the tissues during that time period, but it was an outcome, a consequence of the perfusion process itself. And so the
Yeah.
question that arose in my mind was, well, if it's a consequence of the perfusion process itself, why do they have to start the procedure right away necessarily? Couldn't they start the procedure, say, a few hours afterward? And yes, there might be some deterioration that happens, but it's not an irretrievable case at that point, because the damage from the perfusion process wouldn't have started until the perfusion process began. Would you agree with that assessment?
Yeah, so that's interesting that you mentioned that conversation, because I was just saying it's like, we're talking to each other sort of in really good and constructive ways. I thought that was kind of a spicy conversation, because Greg Fay said like, well, that's all good and well, sort of this Nectome paper, but it's not necessarily always consistent with the rest of the literature. I mean, there have been, dogs recover with long-term recovery after 60 minutes of ischemia. Sort of if your paper would be right, that would not be possible. And there's other literature that shows even longer periods. So that is, I think, a topic of debate. So you can sort of wonder sort of how well that paper is aligned with sort of other papers. And then to the other point, it's like, it also depends how you perfuse, right? And one thing I want to mention, because that is, I think, where often there's a lot of confusion, like the state of the brain and that sort of ischemia induced problem with perfusion. And because these things are actually separate issues, like after, well, let's say an hour. After an hour, the fine structure of the brain, at least what we think encodes memory and identity, is still fairly well preserved. Of course, you see evidence sort of edema and so things. I mean, the first lab of my paper was actually a very comprehensive study into what happens to the fine structure of the brain after various periods of normothermic ischemia and cold ischemia, and so we compare that. So on that front, I'm relatively sort of optimistic, especially given sort of this concept of information theoretic death, right? It's like, okay, it's maybe no longer viable, but when we look at it, we can infer from the damaged state what the healthy state is. But the perfusion issue really pertains to the vessels and the delivery of the agent, right? So it is possible that the state of the brain is in pretty good shape, at least by, ultra-structural criteria, but you cannot get that perfusate delivered effectively. And my lab and other labs have tried a lot. It's like higher pressure, lower pressures, adding clot busters to it, making the solution very hypertonic, throwing different kind of molecules in it, opening the skull that to allow the brain to swell. I will say that is one of the toughest problems of practical cryonics. I would say practical biostasis, because this problem is the same for the chemo people, that we sort of still have to crack. There is a lot that happens to the brain in terms of the circulatory system, microcirculatory collapse and swelling, that does not allow you to deliver that agent. Now, I do agree with Greg. I don't think that those restrictions are as time sensitive as I think Nectome sort of is presenting, especially if you use different ways of doing perfusion. But when you have someone who is down for a long time, clearly, I don't think there is a very good perfusion technique to get whatever you want to get to all parts of the brain. And that's why the chemopreservation people, if you go that route, Nectome doesn't go that route, right? They say we don't do those cases. And then at Sparks, they just say we take the brain out and immerse it, right? Because if you immerse it in the fixative, then you're not dependent on these vessels that sort of have collapsed and sort of all that clotting. So if that makes sense.
Yes, that does make sense. And to me, it's an important discussion because if there is a broader time window, then this whole approach of relying on medically assisted dying essentially would not be necessary even for the chemical fixation paradigm, because if they could wait a little bit longer and achieve mostly good preservation, and I don't think in any cryopreservation or uh, aldehyde stabilization today we could guarantee 100% quality of cryopreservation. But if the difference is between, say, 99% and 97%, whatever the case may be, but one doesn't have to deal with the whole legal and ethical morass of the medical assistance in dying, there could be perhaps more acceptance even of the aldehyde stabilized preservation approach if there's a broader time window like that. And they could take more cases at Nectome as well. Now, the Sparks approach doesn't necessarily run into that particular issue, as you mentioned, because they just immerse the brain in the fixative. The question that arises there is one of reversibility as well. And that was a question that I asked the panel. And I used a kind of, let's say, rough type of comparison. I asked, is it a difference between, say, revival from vitrification being achievable 100 years from now and revival from the aldehyde stabilized preservation being achievable 102 years from now? Or is it a difference between revival from vitrification being achieved 100 years from now and revival from aldehyde stabilized preservation being achieved 500 years from now? But of course, one could adjust the time frames in both examples for both approaches and still get at the essential issue that I was asking about, because the chemical fixation forms all of these crosslinks and one would need a technology to reverse the crosslinks. So how likely do you think that that would arrive close to the time when it might be possible to effectively revive vitrified patients?
Yes, I think that's such an excellent question, right? Because it forces us to really confront this question, like when we're preserving in both of these approaches, what we are exactly doing. And one thing that sometimes I think happens when people look at chemical preservation, they think that it's almost sort of like a photo of the brain, right? But it's not, as you indicated. These chemicals cross-link every molecule together, and at least let's hope that they do. And if you look at electron microscope image, you don't see that, right? You would have to go to a much higher magnification, and then you would see, okay, in chemical fixation, I think they're probably right that everything that matters is preserved, but it's also chemically modified, right? So you cannot say, and I would even say that's fact, you cannot say like, oh, in traditional cryo, you modify, or you can call it damage, like the tissue, and in chemical preservation, you basically take a photo by perfusing a chemical. That's not what you're doing. You're modifying also the tissue. And that raises a really interesting question, how you think about revival technologies, right? If you think about biological repair, and this is something that has been sort of increasingly recognized now, I think, in the broader biostasis field. Historically, chemopreservation was associated, right, with mind uploading, substrate independent minds. That's no longer sort of really the case. Maybe it's still the case in the sense that other people are driving it. That is sort of the revival method that they prefer or have most confidence in. But it's not mutually exclusive at all to do chemical preservation and do a Freitas Merkel style revival, right? So you basically have that patient stored at probably some kind of lower temperature as well. And then these nanobots, sort of another thing they need to do is break up sort of all these crosslinks and then do the same sort of revival thing as you would do with traditional cryo. So if you would do a biological nanotech based repair revival, there should, I cannot think of a very exotic argument otherwise right now. I think there should not be a difference at all in timeline, right? Okay, so that's on the one end. If you believe in substrate independent mines, or just, you know, doing a scan of the damaged state, maybe, I mean, this is here it gets really interesting, because you could do that with a traditionally cryopreserved sort of patient as well, and do a scan and then sort of, you know, infer the damage state and then sort of revive in silico. So you could argue maybe that is where the timeline also would not be different. I think maybe some of the chemo people would say it's like the way chemopreserving brains are prepared is exactly how you would prepare brains for, you know, producing the connectome, right? So you're already sort of doing sort of that procedure. But I have a hard time actually coming up with scenarios where um, these two different approaches yield very different timelines for revival attempts. There certainly is a difference in revival timelines between, well, maybe between biological molecular repair and, you know, digital reconstruction and revival. But that, I think, pertains sort of to both approaches, right? And this is sort of a really interesting question, and almost a philosophical one, right? If you believe in substrate independent minds, mind uploading and so forth, yeah, maybe then you're like, all this all this repair at the molecular level is just all sort of a waste of time, right? We do a scan, repair things in silico, and, you know, with enough advanced AI, we just sort of turn it back sort of on again. So I think it's not so much that the timelines are different in terms of what the technologies entailed in terms of preservation. I think where timelines may differ is really in how you're going to attempt revival for any kind of metabolic sort of arrest.
Yes. And these are fascinating observations, in particular, that you think that the revival of the biological organism, if that were the approach to be attempted, could be achieved on similar timeframes between vitrification and the chemical stabilization approaches. So that is fascinating. Now, in terms of my preference, and I think I've made this known on various prior salons, I would want the biological body or brain, whatever is preserved of that person, to be revived, because philosophically that provides the greatest likelihood of the continuity of what I call the I-ness, the subjective vantage point of that individual. Whereas with substrate independent minds, you could have a very convincing copy that may even be conscious and have the retrospective memories of that individual. But the person who went into the suspension would not come out of it and would not perceive the world through the vantage point of that newly uploaded mind. There have been some advances in that kind of mind uploading. I attended another workshop by Michael Andreg of a company called Eon, and he was displaying simulations of a fruit fly whose brain had been scanned and uploaded. It was a destructive upload, and the fly existed in this digital space, and it was able to move around and flap its wings and display fly-like behaviors on screen. Michael Andreg was even talking about creating some sort of body for the fly, a kind of drone-like body, so that it could move around in physical space. So that would be interesting. Now, I do not have any confidence that the subjective vantage point of the original fly was preserved in the digital fly, that the original fly's direct experiences of the world continue to exist through that digital version. But it is a fascinating project from the standpoint of just understanding the connectome of the fly, being able to reconstruct the workings of the fly brain, and in terms of the contributions to neuroscience, I think that's invaluable. But again, to do that with humans raises questions of continuity of the sort that make me greatly prefer the biological revival pathway. And Daniel Tweed points out this is the Star Trek transporter problem. Yes, if you're disassembled atom by atom and reassembled, is that still you, or was the original you destroyed? Now we have another interesting comment. Yes.
Yeah, I think one thing about that, it's to me, it's always surprising that maybe that is some kind of sociological clustering. It's most people who believe in substrate independent minds also think there is not also don't think there is a copy problem, right? But they are conceptually different, right? You can think like, oh, consciousness, emotions, whatever can run on a different substrate, but a copy is not me, right? So it's always really interesting to see how these two perspectives tend to cluster, that the people think it's no problem to mind upload and the whole copy problem is just and on that note, I mean, if you would do a substrate independent minded revival by scanning the cryopreserved person, yeah, it would be bonkers to just throw that person sort of away recklessly, right? So at the very least, you were like, okay, let's calm down here. Sort of, let's see. I mean, I think I may have once or twice people, oh yeah, just do a destructive sort of scan of the cryopreserved body and just throw it in the trash, you know, like, yeah, okay, I hope I'll see you ever again, you know. But at the very least, you would expect people would go about it in a prudent way, right? And that raises a sort of interesting topic that we cannot really break down. I want to just mention it briefly, is to what extent cryonics organizations should honor revival preferences, right? Because now we think we have very informed beliefs about what the future will entail. And then we say, oh, revive me in this way. But maybe 50, 100 years from now, then we're like, oh no, what were they thinking? That was really stupid. I mean, it's hard to imagine cryonics organization just, you know, pulling through and saying, oh, we're going to do it anyway, right? So how cryonics organizations have to deal with revival preferences is a really good question. Or you might even have a situation where one cryonics organization, so yeah, all these people are mind uploaders, and they're like, yeah, you must be really stupid to attempt biological revival. And another organization focuses more on sort of you know, Freitas types or atom by atom reconstruction, right? So it's really interesting to see how that will evolve. But I think one thing that everyone, I think, can agree on is like all this modeling in silico is going to be very useful and powerful for the revival, even for biological revival, because I've written about it as well. I coined this phrase called reconstructive connectomics for sort of the discipline that takes sort of a damaged brain and then infers the original state sort of in silico, and that can be used as a template for biological repairs. So I think all that work that's going on with sort of, you know, the connectome and scanning is going to be very powerful, regardless of where you stand on a topic like substrate independent minds.
Yes, and I think you make a good point. That is, with the biological revival approach, because there will be some damage to the brain, there would need to be some inferences made and a really good understanding of the connectome, and how, if you think, say, this person had this particular memory and it was documented, but you don't see a counterpart for it in the brain structure, how do you reinsert that in there? I think a lot more study of that will be necessary. So I do consider that extremely valuable work, just like forming any sort of model of the human brain or the human connectome is extremely valuable work. And this is why when I'm asked, for instance, about Robert McIntyre, or now it's Aurelia Song, who essentially originated this breakthrough with the aldehyde stabilized preservation and essentially demonstrating how well it preserves the structure of the brain. I always try to comment beyond just whether that's the best cryopreservation approach. I think of the value of that to the scientific understanding of the human brain and the structures of the brain, and hopefully in the future, which of these structures correspond to which parts of memory, of personality, how that can be faithfully preserved. So definitely very important work. We have some comments from our chat. More life, please, asks, but was it really, really, really the same fly? And he says his intuition is no. Super Fin Guy says, if you can have two copies existing at the same time, that means the copies are not the original person. Well, I would say if the original is preserved and a copy exists, then the original could still be the original person. That's almost tautologically true. But the new copy would not be the original person, even if he or she thinks they are the original person.
Yeah. Well, it would be interesting, right? Let's say you do a substrate independent revival, but then also you would also revive the original cryopreserved body. So what does that mean in terms of identity, right? That is sort of these are the questions sort of boggle the mind for sure. But I think one thing that is really good of sort of the chemo people, they really put, you do need to have good ultrastructural preservation on the map, like a lot more than it was done in the past. Like Cryonics used to be a lot like, oh, good cell viability and so forth. And one thing that we have been founding, and I've been seeing in my lab as well, we used to think that, well, if you have really good viability, that must entail good ultrastructural preservation. And what we're seeing right now in brain preservation, that may not necessarily always be the case, because these viability assays only capture a part of the way the brain works, right? So I think we should at least be grateful for people putting so much emphasis on optimizing ultrastructural brain preservation, and it's a piece of evidence that now is and should be required for traditional cryo as well. In fact, I'm sort of working on a white paper with Jessica Radley from Nectome that actually makes that argument. It's like, okay, both approaches actually introduce some kind of chemical modification. The way to think about revival, there is a unified framework, and sort of the evidence, at least we want to see ultrastructurally, should be sound for both approaches. No approach can be sort of an excuse for saying, and that's, I think, why Greg Fahey and his colleagues now are also doing these papers, doing traditional cryo and showing, relatively well cryopreserved brains, even in a real Alker patient. That was maybe one of the real cool things that happened, of course, in the last years, right? That sort of brain tissue, ultrastructural analysis of brain tissue of a true cryonics patient made into a paper.
Yes, and this was Stephen Coles, per my understanding. So Stephen Coles died in 2014. He unfortunately succumbed to cancer, but as his last research project, he requested that his brain be cryopreserved, and he essentially participated in determining the protocol for that. His wife, Natalie Coles, actually is a friend of mine, and she talked to me about what happened with him and how he essentially stipulated that he be made one of the co-authors of the paper on the cryopreservation of his brain once that paper got published. And yes, that paper was published quite recently, in fact, and it noted that the preservation quality of his brain was extremely high. So I think of all of the cryo patients, he probably stands the greatest chance of a successful revival in the future. But it's quite admirable what he did, and how even in such a situation, which would be extremely daunting for any individual, he still thought about the scientific implications of the process that would be applied to his brain in particular.
Yes, it's kind of it's really cool, you know, fun attended to sort of to be the co-author of sort of a post-mortem study sort of on your own brain, right? So that is really cool. And hopefully, of course, it all works out and so that we sort of can meet him again. So about that paper, it's also like to the brain biopsy that they did, it's like it's coming sort of more important in the field right now to take these kind of sort of samples in general, right? That you can take very small samples from brain areas that don't have very much sort of identity critical information, and can you subject them sort of to this kind of analysis, light or electron microscopy. And Tomorrow Bio is also really starting to do that. Sort of for every patient, they would prefer to have a set of CT scans, and then also you know, electron microscopy sort of on the brain tissue. So we increasingly get to learn more about the effects of all different scenarios and protocols in sort of real world sort of cryonics. So this is a good example of things that you're, I think, going to see more in general in the field.
Yes, indeed. So we have a few more comments here. First of all, Taylor Mara writes, I agree that improving preservation quality now is a prerequisite to attaining rewarming techniques, but a significant advance would definitely bring needed attention and viability to cryonics. And I would say an advance in either preservation quality or rewarming would do that, as long as the public understands the implications, and as long as the public understands that there are not insurmountable obstacles in either of these realms. Now, we also have some comments from Jacob Cook. Welcome, Jacob. He writes, the copying problem can be avoided through gradual uploading. However, he also recommends reading Michael Cerullo's paper, Uploading and Branching Identity, for an argument that you can exist in two places at once. So that, I suppose, can be a more in-depth discussion for a subsequent salon. But in terms of the gradual uploading, I agree in principle. If you replace one neuron at a time with a digital neuron that integrates into the brain, then you could have incremental brain replacement. The question is, how gradual would it need to be? And my intuition, I'm not a neuroscientist, but my intuition is it should probably be gradual on the time frame of years rather than seconds. So if you have a cryonic situation, obviously you don't have that kind of luxury. Even if you're doing it at the point of revival, you're going to need to revive the biological brain and then perhaps augment it with artificial neurons, sure. But you would need a substantial portion of the biological brain to continue existing at that point, and all of the challenges of that, either breaking the crosslinks or undoing the toxicity of the cryoprotectant, rewarming the body evenly, all of that would still exist. But I agree that those who are revived in the future could benefit from some artificial components, including artificial neurons, to maybe help infer some of the gaps in the biological brain. But anyway, Aschwin, we have a link that you wanted to share, and it is your own Substack. It is enter.biostasis.com, and I will display it on the screen right now. So what would you like to say about that?
Yes, well, it's the name of the you know, the Substack, the blog is death is nothing to us. And if you're sort of familiar with philosophy, right, that's kind of what Epicurus' argument was. So like if you don't exist, you cannot experience that. So sort of why bother, right? So but sort of I use sort of this name for the Substack sort of you know, in a sort of more ironic way. It's like, oh, the work that we do in preservation and aging, sort of death is nothing to us. Sort of we will solve it. But yeah, I used to be a very prolific sort of writer, and I, you know, doing a lot of research. Sometimes that's fallen by the wayside. Sort of my last really comprehensive writing, of course, was sort of the manual that I did. But I really intend to do a lot more, hopefully high quality, sort of technical and philosophical writing. So you know, please subscribe sort of to my Neil sort of Substack as well. And I'm probably gonna recycle some of the stuff, also older writings and things that if people have written on the older Biostasis website, because it runs on sort of the old WordPress engine, which is becoming a little dated. So you know, updating and publishing some of really cool old stuff, which, you know, makes me I think, you know, Mike Perry, of course, recently, you know, one of the great people in cryonics was sort of cryopreserved, and that there's still a lot we can tell about this person sort of on my own blog and the Biostasis standard. I think what is often not really appreciated about Mike Perry is, like, I mean, yeah, he wrote sort of these very philosophical books about, you know, the consequences of physics and quantum mechanics for universal immortality. But in another way, he was also a very practical person, right? Sort of he did sort of the original mathematical calculations for Alco's perfusion circuit, and Mike and I worked on a metric called the SMIX, the standardized measure of ischemic exposure that sort of can quantify, you know, how much post-mortem time, ischemic time, has accumulated in a cryonics case. So there's a lot sort of to say sort of about him. So check sort of all these publications that have been announced sort of in this meeting, because I think you will see quite a few sort of interesting tributes to him. Another thing that is not very well recognized, he was actually a pretty early advocate of being more open to chemopreservation. He was, as probably many people know, very sort of optimistic about the capability of future technologies. And he wrote articles for chemical preservation as a low-cost option. And at the time, he was, you know, sometimes almost sort of ridiculed or not ignored. And I would say his vision has prevailed, you know, like especially if you look at an organization like Sparks Brain Preservation, they're doing exactly what he advocated, sort of having these lower cost chemical preservation options, because he believed it retains enough sort of information, at least for many people, to permit future revival. So that's I guess he was a little bit of a visionary there in a time when it was not really appreciated.
Yes, indeed. And it is a tragedy that the world lost Michael Perry, at least for now. He was struck by a motor vehicle as a pedestrian in April 15th, 2026. And unfortunately, he could not be brought back to life. He was 79 years old, and they performed a cryopreservation on him. Based on the reports from Alcor, it was a high quality cryopreservation, so there is some hope in that regard. And Aschwin also linked to his book here, which I will post the URL for as well. It's available on stasis.com/forever hyphen for hyphen all. The book is titled Forever for All, Moral Philosophy, Cryonics, Scientific Prospects for Immortality. So thank you, Aschwin. And now let us also broach one other field that I wanted to mention today in the salon before we go to another topic, and that is field cryoprotection. So with field cryoprotection, there have been some advances in recent years as well. And I'm hoping that you can comment on the importance of those and how quickly it might be possible now to cryopreserve a patient who might have died in an unusual location, maybe at their home or far away from a hospital setting.
Absolutely, yeah. That's a really important sort of topic. I think something really of the last 5 years, where there has been a transition really from doing a lot of these procedures in the cryonics facility operating room and doing them just straight up in the field, right? And like just to provide a framework to understand sort of why that is such a big deal is like what we used to do in the old days is let's say a person is critically ill and we fly a standby team to, let's say, Chicago, and then if we're lucky we're there exactly at the right time. We do our stabilization procedures, right, the cooling, the medications, but then at most we wash out the blood of that patient, and then that patient had to ship all the way to Scottsdale, Arizona, or maybe to Michigan. And for the last part, the cryoprotectant perfusion. Um, and one of the problems with doing it that way is if you ship someone on water ice, even if the blood is washed out, you still have some accumulation of what we call cold ischemia. Yeah, the patient has a lower temperature that depresses metabolism, but you still get some degree of degradation of tissues, especially of vessels. One thing that happens if you have a patient on water ice for 24 hours, let alone 48 hours, when you start perfusing in the operating room, these vessels will be very leaky, the patient starts swelling, so that's all no good. So at some point, a lot of people in our community converged on the idea of field cryoprotection. Why don't we do that step in the field? And why is it called field cryoprotection and not cryopreservation? And the reason is the only part that is being done in the field is the introduction of the cryoprotectant. The cooling to cryogenic temperatures, that does not happen in the field yet. In theory, it's possible, but that would be non-trivial, because then you would have to sort of fool around with cryogenic temperatures and enormous vessels, at least for whole body. Maybe it's a little easier for brain only, but right now what we're doing is field cryoprotection. And then the patient, instead of shipping the patient on water ice and then accumulating that additional time of cold ischemia and then doing cryoprotectant perfusion, the cryoprotectant perfusion with the agent that inhibits ice formation is done in the field, and then that patient can be shipped on dry ice to the cryonic facility, and that can go either by car, a truck, or it can go by airplane, even from Europe to the United States, or the other way around. In fact, there have been quite a few Tomorrow Bio cases in the United States. And as you know, the Tomorrow Bio facility is in Switzerland. And these were all field cryoprotection cases. And we're gaining a lot of experience with that now, and it's, getting progressively better. So I think that is a pretty important change in how cryonics organizations operate, especially the two major ones, Alcor and Tomorrow Bio. Although if you're a member of the Cryonics Institute, you can contract with Suspended Animation to have these services also added to your arrangements. Yeah.
Yes, very interesting. And for those who want to read more about it, we would recommend Aschwin's article, Whole Body Field Cryoprotection in Cryonics. It was written in 2025, so quite a recent article that speaks of this advance. And really, that does mean somebody who dies in an unusual location or far away from the cryonics facility has a better chance of reaching the cryonics facility in a protected state, not in a complete cryopreservation, but with the cryoprotectant being introduced. So thank you for that. And we have about 10 minutes left in our salon. I wanted to ask you about another area of interest of yours, since we shared that one as well, and that is running. You have been running some major races in recent years, and you've told me earlier today that you had a breakthrough in running recently. So please tell us more about that.
Well, breakthrough. I didn't make a new discovery in the field of running, but yeah. Well, as you say, we're both runners, and actually, I want to compliment you for your meticulous documentation of your races. It's like that has actually been pretty inspiring to me, the way you sort of break them down. So that's great. Yeah, I mean, I've always been sort of a fast runner, but it's really in the last sort of 5 years or so that I started really cranking it up. Maybe it's also like, I'm 52 years old now. It's like, okay, let's see what I can still do relative to my peers and sort of younger people. So yeah, I set myself 3 objectives. One was to run a sub 20-minute 5K, which is very spicy for my age. The other one is qualifying for the Boston Marathon. That as some people know, the Boston Marathon works mostly by qualification, and you have to run like really, really fast. That is adjusted for age, but if you calculate that to a normal, it's like a 20 or 30-year-old people, nowadays you have to run like sub 3 hours to qualify for that. So I would have to run the age adjusted equivalent for that, and sort of I'm on my way. And then the third objective is to run a sub 6 mile, right? So to run the classic mile in less than 6 minutes, what I've been told, and AI tells me so as well, that is a ridiculously competitive time for sort of my age. And sort of yesterday I ran a road mile, and I got under 6 minutes. It was 5:50 actually. Now there was some downhill part in the course, but I take it. And also, like, even the sort of the what they call the grade adjusted sort of pace that takes into account the downhill was still sub 6. So it seems like I've one out of the way, and so I'm training hard for qualifying for Boston. That sub 25K, I'm not sure if that's in the cards. I mean, that is a really hard distance, as you probably know. Sometimes people don't know much about running. They think, like, the longer the distance, the harder. But the 5K is like the 5 kilometer race is really hard and a lot of suffering, because you're not sprinting, but you're getting pretty close to running very fast, and you have to sustain that for like 20 minutes or so, at least in my case, which is gruesome. I usually want to step out when I do so, but I won't.
Yes. Well, congratulations on the 550 mile. That's quite impressive. My fastest mile pace ever is 6:22. So you have done something remarkable, I would say, and it's a testament to your training and the consistency with which you have pursued it. I think a sub 20-minute 5K is feasible for you if you can run a sub 6-minute mile.
Yeah.
I think everything has to come together in the correct way in order to be able to run that fast. Now, my fastest 5K time is just a little over 21 minutes. And I know for me personally, I essentially have to feel ideal to do that and have good weather. By good weather, I mean between about 40 and say 55 degrees Fahrenheit. So a bit cool. So that motivates me to run faster. But yes, a 5K is not easy, but I would say running a mile really fast is more difficult than running a 5K fast. And so you
Absolutely.
kind of
Yeah.
have the speed work baseline needed for that.
It was certainly encouraging, right? Because you can sort of look at, you know, sort of age-adjusted time, sort of how to match up. And as I looked at my mile time, and I went from advanced to elite. I'm like, oh, okay, that is sort of really cool. Yeah, I mean, realistically, I think that marathon time, I think I can do. I think the only problem with the marathon, of course, is you have maybe at most 2 opportunities a year, right? Because I mean, I think distance running is probably would be good for most people. I would not recommend people run marathons for health reasons because they take a lot. I mean, we're not designed to run marathons, sort of, right? And that's also where sort of the weather comes into play. Like you, I'm really not a good hot or even warm weather runner. All my personal records, my PRs are set sort of in really cool weather. So when the qualification period opens for Boston, I have to really think about what are some of these really cool weather marathons in the world. And it's getting harder, actually. It's like Berlin used to be the course where people really run fast, but the last one was like ridiculously hot, you know. So it's quite a conundrum now, sort of to see sort of where I run these things. But yeah, thank you sort of for the sort of encouragement. It's a joy to do. It's very different, of course, from spending time in the lab or writing, but that's actually, you know, why you do it. Although I think fields like that also are becoming very rigorous and quantitative, right? Sort of the way people think about running nowadays, that like, you know, carbon plates, you know, in shoes, and having these lactate threshold workout sessions and then measure it sort of completely. It's like it is all becoming very nerdy, even sort of running. You almost forget that in the end it's just a matter of going out and running a lot, right? There's no substitute for that.
Right. Exactly. And the amount of running practice that one does has a direct correlation with the results. Now, usually these days I will run about 40 miles per week. Previously, when I was a bit faster, I would run perhaps 60 miles per week. And I know a lot of champion runners do even more, but when they train at slower paces than their race pace. So that kind of builds up the endurance. We have a compliment for you from Drain Mag, who writes, Aschwin is an excellent runner, ran a mile in under 6 minutes yesterday. So
Well, I hope she's listening because that's what we just. I was.
yes.
She was on. She was there during that race actually. So, yeah. It's great. Yeah, it's a lot about sort of the volume you put in. I think the reason why I'm optimistic about this Boston qualification is, to be very honest with you, I do not always put this enormous amount of miles in that I should do for marathon running, right? I still get away with sort of a 3:30, 3:35 marathon without not putting in these, 80 miles weeks or so. And I think if and when I do, then you know it, right? The mitochondria, the capillaries, it will become denser. And so I think there's room there. So we'll see. But yeah. I have to run 3:25, I think, to be safely into Boston. So that's also a spicy time.
Yeah, that would be an impressive time, but doable, given
Yeah, yeah,
how you have progressed over the years. I think that would be doable for you. I probably would need to be in my early or even my mid 50s in order to have a chance of qualifying for the Boston Marathon. And I would need to
mhm,
become faster at the marathon than I am currently.
yeah,
But you provide an excellent example of what is possible. And I also appreciate the scientific mindset that you apply to your running. Another person who has inspired me in that regard is Dr. Bill Andrews, who
hmm
now is he's going to be 75 later this year, and he still runs every day. Of course, he's run more than 200 ultra marathon races, and he continues to be in great shape. So, Aschwin, thank you for joining us today. I really appreciate the thorough overview you gave of the state of the biostasis field and the kinds of conversations and research that you've been involved in, as well as a bit about your running progress, always quite inspiring. Any last words before we conclude?
No, my most obvious last words is to thank you for having me. It's, you know, it's always a pleasure, and I appreciate sort of the kind words, and you know, I wish you luck with sort of your initiatives and also with sort of your running endeavors. Actually, I will be running the Las Vegas half marathon in January. I mean, you're in Nevada, right? Or
Yes, Northern Nevada, though.
yeah,
So
you're in
Las Vegas
northern
is
Nevada,
about
right? Yeah.
an hour's flight or a 7 hours drive away, but January is probably the best time to run in
I
Las
know, right?
Vegas.
I've always been fascinated running up and down the strip. You know, that itself is just worth the price of admission, I would say. So I'm excited.
All right. Well, that's something to look forward to. Maybe I
Yeah.
will make it down there in January. And for now, thank you for coming. And to you and to all of our viewers, I hope we can all live long and prosper.
All right. Thank you so much.